Wait, yeah, wait, I forgot about that. Like, okay. Exactly. Like,
I'll miss it when you come.
but like,
Huh?
like, no, right? Not secret.
All right, guys, big day.
Big day. Big day. Oh, no, I'm afraid.
You're not.
Sorry, I did not understand last night.
If you got a question about last night, talk to me. Oh, we never finished this part. Okay, let us. No, all right.
My mom
All right, guys, we did not quite finish this stuff from yesterday, so let me just give you a quick reminder of where we were. I believe we did this one. So again, this is not a super common AP question. I'll have one on my test, or one going from here to the formula, and one going from the formula back to the integral. What is more common on the AP test is you will be given this expression, and with this expression, they ask you one of two questions. One is, they'll say, write this using an integral or some words to that effect, or they'll say, evaluate this. And if they say evaluate it, believe me, you want no part of trying to evaluate that expression manually. So you will change it to an integral, and then you will go about the process of evaluating the integral, which is what we're going to do today. So I've been kind of hinting to that. I've been referring to Chris because he's the only one in C that actually has done that, but we're going to do that today. It's not a big deal at all if you know your integral rules. So I'm just going to give you, we'll call it 3B, and I'll say, all right, what if you went from -3 to 5 of the equation x squared minus sine of x dx? And the question was, can you rewrite that using this, this sigma limit notation? So what do you start with? The limit as n goes to infinity of what? The sum of all the rectangles, starting with what? The first one, I equals 1, and going through the last one, which is n, but we know that n is infinity, so the infinity is going to get plugged in there. And each of those rectangles is created by a what? A base times a height. So the base is always the total length of the interval. So 5 minus a -3 is 8. So my base is going to be 8 over n, because there's an infinite number of those rectangles. And then my height is what? Technically, my height is f of what? Y'all need to focus. F of what? So what would be the first value I plug into my function to get the height? You're starting at -3, but do I plug -3 in if I'm doing a right rectangle? No. So you say, well, I would look at -3, but then I would add what to it? I would add 1 base over, which is 8 over n. But because I'm going to keep doing that, keep adding 1 base over for the first height, and then 2 bases for the second height, and then 3 bases for the third height, I put an I in there representing 1 base for the first height, then 2, then 3, then 4, all the way through infinity. So how do I finish this? I take that, plug that into my function, which is this. So I put a big parentheses and say, blah, that squared. That's the that squared minus the sine of that. And then end the parentheses. And that is how you go from a from an integral notation to this notation. And I think I worded it here as Riemann sum notation, but it would be something to that effect.
How do you get the 8 over n again?
That is my base. You know how normally when I'm finding a base with Riemann sums, I go 5, the ending place, minus the initial, and then I put the number of rectangles, and that's my base? Well, the number of rectangles is going to infinity, so I have to put an n there because I can't put an infinity in there. And that's it. And if I had to do this manually, it would be an absolute nightmare. We're not going to do that, so we would leave it. That would be the answer. Or so, there would probably be a bunch of answers that looked very similar to that. And again, could I have an I equals 0 right here? If I have an I equals 0, what does that mean? If I is 0, what do I end up plugging into the function? And that would mean that I'm starting with the left side. So if I had a 0 there, what would that represent? A left rectangle approximation. But if I start with 1 right there, then I'm saying I'm not starting at -3. I'm going 1 base over and then into the function. That would mean a right rectangle, because that's the initial height would be the right side of that first little rectangle. No, it doesn't. If you did it manually, when you go to infinity, remember, the base I add is so small. Like say I'm standing right here at -3. What happens when I don't add a base of 0? What happens when I don't add a base? I plug -3 in, right? That would be a left rectangle. I'm starting with the left side. What happens when I step over a base that is so small that it's almost 0? What am I plugging in? Still -3, because I've added almost nothing, right? And if infinity goes in there, what's 8 over infinity? So tiny, it's like nothing. So we're talking about it really doesn't matter when you are approaching infinity. It's an abstract notion. I realize that it's hard to wrap your brain around approaching 0. Am I there? Am I not there? Doesn't matter because the calculus takes care of that. But that's the idea, is we are approaching infinity. So even when I do a right rectangle and plug the right side in, if the base is so small, it's almost nothing. The right side of that and the left side of that are essentially coming from the same spot. So it doesn't matter mathematically. You won't see that because we're never going to do this. We're never going to do it algebraically. We're never going to do that. We're going to go, wait, I hate that. I'm going to change it to this and integrate that with my integral rules. Now, if I go to this, this is saying that this actually just said, write the following as a definite integral. The only reason I'm stopping there on this problem is because we technically haven't learned how to do a definite integral. That's what we're doing today. So what we're going to do is stop short of simplifying, but on an AP test, it's probably a whole lot easier for them to say, simplify this expression. So the first thing we're going to do is go, oh yeah, that's that ugly integral expression that Newton came up with, but some other smart guy, maybe Newton, somebody else, I haven't researched it. Somebody else went, hey, there's some tricks to integration. We're going to learn these tricks, and then we won't have to ever do this again. But the integral of this, the expression that represents this, the expression would be the integral, yes?
I looked up what you came up with the integral rules, and it's for like
Leibniz, the German guy?
It's that guy.
Okay.
That you were talking about.
So yeah,
And Newton, like they both.
Yeah, they were both at different locations in the world doing the exact same thing, and nobody knew it at the time because there wasn't Twitter, right? But later on, when they looked at their works, they're like, hey, they published these almost simultaneously. Yeah. So Newton kind of got credit because he was a little bit more familiar to the. I don't even know the story. I probably should look it up, but. Oh yeah, yeah. I actually haven't looked at the story. I probably should. All right, but let's look at this, guys. So right here, I'm going to say an integral. What do I have to have? I have to have the beginning, the ending, where it started, where it ended in the function. So can anybody tell me where this thing started based on what you know? It starts at 1. Why? You can see the 1 right there. The first thing I usually do, honestly, is I look at the base. Anything over n is my base, and the base shows up twice, right? It shows up once outside the function, and then it shows up again inside it with an I. So what I do is I go, okay, the part on the inside with an I, that's always added to the initial location before you plug it in. So the initial location must have been a 1. That tells me there's a 1 on the bottom. Now, what does the number above the n represent? The what? The distance between the beginning and end, right? It's the b minus a. So if I know that's 5 and I'm starting with 1, where did I end? 6. So now I'm 2/3 of the way there. Now at this point, remember what I've been doing. I've been having a base times a function. So to make my brain clear, I'm going to go and get rid of that base. Not the one that has the I, that's part of the function, but the one that's just over n. I'm going to cancel it out, and then whatever's left there is my function. But what does this represent? The x. So I look at that and I go, oh, this must be 4x squared. So my integral is 4x squared, and don't forget your dx. And then today we'll learn how to actually do those and actually get our numerical answer. Because that's positive 5. Because you always, to find the base, you always go b minus a over n. So if it was b minus a and you had a negative number up there, yeah, then I would go 1, right. Well, negative, well, yeah, if it was 5, I would have negative 4. Because that would subtract 5. But if it's positive, I'm going to add 5. Yeah, that's a negative. Yeah, you don't really see that. It's a good question. I don't know that I've even seen that. Maybe they just think, oh, that might be a little bit too tough. But I don't know that I've even seen a problem where that's a negative there. But if it was, then definitely, yeah, because you're always adding it. So if it was a minus, that would mean you're subtracting it. Just go the other way. But yeah, I don't have any recollection of that. So so look over at this one. What do you see over here? Well, you're going to start with an integral, right? Where do you look? Where do you begin? At -1. Good. You can see that because that base times I is being added to that. So I'm starting at -1. What's the distance between my A and my B? 3, because 3's are on the top of those ends. So I'm going to add 3 and get to 2. And then now I need my function in there. So I'm going to take the base part that just has an n, this right here. I'm going to get rid of it so I can kind of see it clearly. And what do you see? Blah something cubed. So x cubed, don't forget your dx. All right, look at this number 6. Okay, number 6, you see that? You go, oh, the limit sigma stuff. I remember that. So I'm going to throw down an integral. What is my a value? Can you see it? 4, because you can see 4 is added to the base times I. So I'm starting at 4. Where do I end? 7, because the number over the n is 3. And then to avoid any confusion, I take that 3n that doesn't have an I get rid of it, and I look at the rest. So what do you see left? E to the 2 blah, so e to the 2x. Don't forget your dx. And when you integrate that, don't forget u substitution, right? That's not e to the x, so you got to put a u in there for the 2x and adjust. How about this? Integral, where am I beginning? Again at -1. What's my distance from A to B? +7, so I'm going to add 7 and end up at 6. And then I'm going to get rid of my base over n. And what do you see here? 3 blah squared plus blah, 3x squared plus x. So parentheses 3x squared plus x, end it with the dx. And last but not least, number 8. Oh, by the way, then I'll answer your question. One quick thing. Sometimes, because n is technically a number and it's not changing, it represents the same huge idea. The I is the thing that's changing. 1, 2, 3, 4. That 3n occasionally will show up out here. Like they'll write this problem like this. Because we are allowed to factor out constants. We are allowed to do that. So if you were to ever see something like this, don't let it bother you. It's not very common, but it's possible. You'll be like, why is it here? Oh my gosh. No, it's considered a constant, right? A very small, tiny constant, but it's considered a constant. And constants you are allowed to factor outside of a sigma. So again, not very common, but sometimes that will be located in different places. Don't let it bother you. What's your question?
So does the 3 over n, what you're just talking about, does that represent the dx?
The what?
The dx. And like,
Kind of. Yes, because dx means change in x. We're going to talk more about that as we start doing area and volume. And the change in x is the width of the base of the rectangle. And that's kind of what we're doing there. Yes. So this one starts at 0. Do you see why? Because all you're doing is jumping straight to 3in. You're not adding it to anything. So you must have been adding it to a 0. So in the absence of seeing a number, put a 0. What is your, you're going from 0 to what here? 3, because the 3 in the numerator. And then again, I'm not getting rid of the 3in's, just the 3 over n. And what do you see left? 5 blah squared minus 2 blah. So 5x squared minus 2x. Don't forget your dx. All right? So hopefully you're good with that. Again, once you get it down, those aren't overly tricky, I don't think. It's just a matter of understanding how to move back and forth. I'm not going to revisit that again unless you ask me something. So don't forget to look over that for this test, because we're about to kind of get away from that. And people forget to look over it and they miss easy questions, in my opinion, relatively easy. All right, so here we are today. First fundamental theorem of calculus. Probably the singularly most important thing we'll do all year. It's not difficult in terms of what most people think are difficult. In fact, if you know how to integrate, you're going to already know how to do this. So like I've been mentioning before, this integral can be represented with this limit, this sigma notation. But we don't want any part of that. Okay, and you'll never have to manually show that work on an AP test. Okay, maybe in some Cal 1 class at a university it's possible, but I don't remember ever doing that in college, to be honest with you. I just remember doing integration using our rules. But anyway, here's the idea of the fundamental theorem. Okay, now there's a proof to this. We may go over a little bit later, but right this instant, I just want you to see what you do. So when you see an integral before today, you never saw the a and b on there, and you just integrated into what? Whatever new function you got, and what did you always tack on to the end? Plus c, okay? So that f of x stands for that new function plus c. Now, the way we do this, when we integrate, and you need to have good form, more people miss more points on the AP test by not showing good form. So your form, when you have numbers there, you do the new function, and then you put a vertical line, and you recopy a to b. Or you jump straight to big F of b, big F of a. Now, to remind you of something from the other day, what if I had an integral that had an f prime of x dx? F prime from a to b. When I integrate an f prime, what do I get? An f. So I would write, okay, you're getting some new function f from a to b, which ends up being little f of b minus little f of a. So the only reason I'm using big F here is because this was a little f, and I don't know what comes before a little f in terms of the whole derivative lineup. So I go, well, some new function that is related to little, and it's common practice to use big F in that regard. And if you saw f double prime, what does that integral become? F prime, and therefore you have f prime of b minus f prime of a. Are you with me? And we have been saying over and over, if this f stood for a rate, when you integrate a rate, what do you get? An amount function. So this amount function from a to b means the ending amount minus the beginning amount. And ending minus beginning gives you the change, right? Right? I have $2 and I work hard, now I have $100. My change in my work, my change in my amount was 98, right? Ending minus beginning. Are you with me? Okay, so I want to show you a couple things right here and just kind of build this process here and talk about area and why it means area. So right here, here's my velocity function. Let's just pretend I told you the velocity was 3. So velocity is always 3. Maybe it's just somebody walking at a constant pace. I don't know. So here's my v function right here. So right here, velocity is 3. There it is. Okay? Now, if I integrate a velocity, if I integrate from what we know right here, a velocity function, dt, from 0, we're going to go to 4, from 0 to 4, what should I get when I integrate a velocity? Well, if I take a derivative velocity, I get acceleration. But if I integrate a velocity, I go back to position, and we know it would be a change in that position because my position function, right, would be going from 0 to 4, right? And according to my rule, I would go position at 4 minus my position at 0. Are you tracking with me? Now, what do we also know? We know that an integral represents the area below the curve. We've done that with accumulation, right? So if I looked here and said, I could also find my position by just looking at this area, very clearly, I get 4 times 3 equals 12, right? So my change in my position should have been 12 units if that's a velocity function. It should be. Well, let's check the math of that. What is this line right here? 3. So I'm integrating 3 dt or dx, whatever, from 0 to 4. How do I integrate 3 with your rules? When you integrate a constant, you get an x, so 3x plus c from 0 to 4. So this is me using my integral rules. I integrate the 3 and get 3x plus c. And then my fundamental theorem says, take that from 0 to 4, which means find your new function at, find your new function at 4, and then find your new function at 0, complete that, and subtract. And what do I get? Well, the c's, because I distribute, end up canceling, and I get 12 minus 0. Why does that say 3? How has nobody caught that over the years? So 12 minus 0 is 12. Are y'all seeing that? So what we just showed is 2 different ways, one by finding area and one by using our integral rules to actually calculate a derivative, and they both held up. Let's look at a little bit more complicated one. What if I told you this was the function for velocity? 1/4 t plus 2. It kind of looks like a linear function. This is the 1/4 t plus 2. But this time I want to find the area between 2 and 8. Now, if I asked you to find the area between 2 and 8, right here, what would you do to calculate that? You personally. Trapezoid? Okay, so if I wanted to find the trapezoid here, I'd go 1/2 times the base, which is 6. I'm just going to do one big trapezoid. The left side is what? It looks like 2.5. How do I know it's at 2.5? Think about it. How do I know that? Because I could do a similar triangle, couldn't I? Or I can tell if this thing is going rise 1, run 4, that's the same thing as rise 1/2, run 2. So I must have risen 1/2. So I think I know that with confidence, but if you're not sure, you could say something like, all right, 4, 1 is similar to 2x. And you can say 4 over 1 is similar to 2 over x, and you can cross multiply and solve and get x as 1/2. So that must be 1/2 right there. Whatever you need to do to make sure, but be careful, because sometimes the slopes are 1/3 or 1/5, and they're not quite obvious. So what is my first height? 2.5. What is my second height? 4. And when I calculate that right there, I get 2.5 and 4 is 6.5. 6 times 6.5 is 39, and I get 39 halves. Sure enough, that happens right there. Now, let's check it using our rules just to make sure we're okay, which I think we all believe that. But if I said, forget accumulation, forget actually calculating the area, let's just use my integral rules. What is the integral of 1/4 x plus 2? Well, there's a plus, so what can I do with these two parts? Integrate them separately. So what's the integral of 1/4 x? 1/4 x squared over 2. So x squared over 8. What's the integral of 2? 2x. Now, why do you think I didn't bother to put plus c there? Because you saw before when I put plus c, this one would have had a plus c. This would have had a plus c. This would have had a plus c. But when I distribute, that becomes a minus c, and they cancel. Well, I get sick and tired, as does the rest of the calculus universe, of writing c and canceling them. So when you're doing a definite integral, you don't have to do that. It's understood they're going to cancel. You can completely ignore that part of the process. So you'll notice I took my function. I didn't put a plus c, but I recopied vertical line 2 to 8 and then showed my work. Or I actually physically plugged the 8 in to show that, minus physically plug the 2 in to show that. I have to show the AP reader either this step or this step, because they're going to give you a point maybe for the setup, a point for showing this or all of this, and a point for your answer. So if you only write an answer, you're getting 1 out of 3 points. You're like, that's a ripoff. Well, complain to the AP board, but that's what they're giving you points for a lot of times. Now, not on a multiple choice. Do what you want to there. So all I got to do is simplify this part, and I get 8 plus 16 is 24. Simplify this part, and I get a half plus 4 is 9 halves. Subtract 4 and a half, and I get 19 and a half, or 39. Squirrel. All right.
It's like that.
Well, don't you ever get tired of
Did you
teaching
know
the same
you
lessons to
can
6 different classes? Or do you just
I have 3 different classes.
You can make music.
Oh,
or
I'm
math.
fairly tired of it, yeah. But it's the people that changed it.
well, don't you?
And it's 99.9% sure my last year I'm teaching 6 classes, so I
Are you
see
doing
0
a
chance of being here
retirement
full time. Yeah, I'll retire, and if they need me for a couple classes, I might roll in here in the morning. But
You also said that last year and before that, though.
oh, I've already talked with Henry about that.
Oh, really?
Oh, yeah.
Oh, that's exciting. Well, you stayed for
So,
us.
yeah.
You stayed for us.
What?
Thank you.
That's the big question. I don't think Helmer's wants on after classes. He could easily do these, but we'll see. All right, guys, I'm going to show you the proof of this. I'm going to confess, actually, I didn't even look over it. The proof can be a little tricky, but I don't care. You're never going to have to do this proof. All right, so just rest assured, take a deep breath. Don't worry about the proof. If a calculus teacher ever makes you do this proof in college, then that's, oh well. It's not lovely, but I'm going to show you the logic that Newton used here. Okay? So, and you got to just stay with me. If you get to the end of this and you're like, all right, that's bizarre, but that kind of does make sense, then I've accomplished my goal. If you get to the end and you're like, I don't know what you're talking about, it doesn't matter. Okay, for those that actually kind of care, I'm throwing it out there. So let me ask you a question. Does it make sense right here that I'll tell you what. Does it make sense right here that the area from A to X, now this would be the area under the curve from A to X, right? This first part, plus the area from X to X plus H. Well, there's X, and there's X with a little extra part, X plus H. That's the area right there. Does it make sense that that's the same thing as the area from A to X plus H? That makes sense, I think. Okay, we're off to a good start. One step down, right? All right, 2. With regular algebra, could I take this area of A to X and subtract it from the other side just because of algebra rules? Look at that, 2 rules down. Okay, now, right here, does it make sense that H, which represents what? This little bitty part right here, that H times the minimum F value right here. So right here, if I took this H, that distance, times the minimum F value, right there, what do you get? H represents a what? A base. The minimum F on that integral represents a what? Height. So base times the minimum F, wouldn't that give you, stay with me, wouldn't that give you, say, that area? Base H times the minimum, the smallest F in that region would be this. So does it make sense that that area right there, okay, that area right there, and I'm jumping over here, H times the maximum F, right? So H, stay with me, H times the maximum f would have given you that area. Are you with me? The whole thing? Does it make sense that stay with me right here. So there's the minimum, the smaller, like this left-handed rectangle, that's like a right-handed rectangle. This represents the area from A to x plus h minus the area from A to x. Isn't that the real area there? So doesn't it make sense that the real area is a little bit bigger than the smaller rectangle and a little bit smaller than the bigger rectangle? Does that make sense? So, okay, so if that's true, then let's look back up here and go, well, the area of the the area of the whole minus this, that right there, okay, this right here, hold on, give me 2 seconds. Oh, so now I'm going to take this whole thing right here, since it kind of made sense, and I'm going to divide everything by an h. Dividing all 3 parts by an h cancels those h's and puts an h there on the bottom. Are you with me? Now, if you're with me already, look, we're 4 parts in, and we're false. Okay, now, what if I took the limit of this, and the limit of that, and the limit of this? Now, let's hold on for a second. What does this look like? Limit, and I'm just going to kind of give you a hint. The limit as h approaches 0 of x plus h minus x over h. Sounds like a derivative function, doesn't it? Okay, so this little part right here kind of sounds like a derivative function. All right, we're going to hold on to that thought for a second. Now, tell me this. What happens to the limit of the minimum f as h goes to 0? Now, think about it. Here's f. What happens as the h part shrinks to 0? What does the height become? If there's no h, then you're just plugging an x into the function. What do you get? You get an f of x. So this becomes f of x. Now, what happens to this maximum part? Again, doesn't really matter though, because as h goes to 0, what happens? Becomes f of x again. So the left side and the right side, if the h goes to 0, both become the same thing. And this is where something called the squeeze theorem comes in. If I told you that there was some number that was bigger than 3, but smaller than 3, what do you know it is? 3. Well, I am now telling you that there's something here that is bigger than f of x, but smaller than f of x, which means that it is f of x. Hey, that's where I am now. Are you with me? Now, back to my comment about the limit as h goes to 0 of x plus h minus x over h. That feels like a derivative. So this right here means the derivative of the area function from a to x, because the h is shrinking to 0. So if that's the derivative of the area function, then that's the same thing as f of x. Okay so far. I know some of you might be spinning a little bit, but okay. Now, at this point, what if I decided to integrate both sides? What do you think happens when I integrate a derivative of something? The integral and the derivative do what? Cancel, leaving me this. But when I integrate the f of x, what do I end up getting? A new function, big F, plus a c. Okay? So what this is saying is that the area from a to x can be represented by a new function plus a constant, given that f of x represents the antiderivative, but we've been saying that for a couple of days. Okay? Now, what happens if your x value was the same as a? Then what would happen if I plugged an a in here? What is the area? What did we ever say that the area from a to a was? 0. So if I went from a to a, then that would mean that 0 equals f of x plus, if I plug an a in here, that would mean that 0 equals f of a plus c, which means c is negative f of a, right? So I could take that negative f of a and plug it right here, and I would have the area. If I plug it in right there, this right here, plug it in there. If I plug it in there, I would have area equals the f of x minus f of a. You seeing that? And if area equals f of x minus a, and you already know that you can find area from a to x of a function by using an integral, then that means the integral from a to x is f of x dx is f of x minus f of a. And just to show that this could be true for any x, I just let x equal b, boom, boom, and I have my first fundamental theorem. Now, somebody way smarter than me, maybe or maybe not way smarter than you, came up with this and proved area integration. But somebody else came along, maybe it was Leibniz, came along and came up with all those little rules so we can stay away from that sigma notation limit junk, okay? I'm very grateful for those rules. Same people that came up with the derivative rules, probably, they all are linked together. So from here on out, as long as we know that big F is the antiderivative of little f, then I can use my integration rules or my antiderivative rules to get this function, plug in the b, plug in the a. Now again, you don't need to know this. I just wanted you to see it because I hated when somebody told me something and said, just trust me. It's like, ugh. If you're taking regular physics now, there's so much a part of regular physics that has to do with calculus that ends up getting a formula and you're like, where does this come from? Well, it doesn't really make sense for me to explain. And it was always annoying to me until I got to physics 2 or what y'all take and see here. And when they do the calculus explanation, you're like, oh, well, that makes sense. It's a rate of change of a change or whatever. Rate of a change. All right, so with that in mind, blah, 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 I got some Newton stuff going on. I did want to mention again, the whole when you integrate a rate, you get a change in the amount. But when you're dealing with units, guys, check it out. If you integrate something that was like meters per second squared, when you're done integrating, meters per second, right? Because this is a rate of a rate. When you integrate a rate of a rate, you get a change in the rate. When you integrate a rate, you get an amount, change in the amount. So the units, it's almost like you're just knocking off one of the denominators, knocking off one of the denominator values whenever you integrate. Same when you take a derivative, you're adding, right? Start with meters, then meters per second, then meters per second squared, and I guess meters per second cubed, if whatever the heck that means. You can keep going with that as well. All right? Now, let me show you a very, not super common, but an error I see. Can anybody catch it right here? I see this all the time. What did I do wrong? I integrated from 1 to 4. I plugged the 4 and I plugged the 1 in. I got 63. Why is that wrong? I didn't integrate. I literally forgot to integrate. I see that more times, and I'm like, guys, got to integrate. Don't forget, we got to integrate first. I got to take this x cubed and I got to make it x to the 4th over 4, then plug the 4 in there, and x to the 4th over 4, then plug the 1 in there, right? 4 and the 1, and then simplify. So don't forget to actually integrate before you apply the fundamental theorem. All right? And I think most of the rest of this stuff is just talking about use substitution. One little other thing that they mention all the time. Every now and then, for instance, somebody will give you a problem that looks something like this. And we'll do a lot more with this, but right here, it says integrate a to b of f of 3 of x dx. Now, what does your fundamental theorem say? Your fundamental theorem says when you integrate f of an x dx, it's big F of x from a to b, right? But if I don't have a single x there and a single dx, and I have something different, like 3x, 5x, 2x squared, how do you make it match this? Use substitution. It is amazing how many people that will do this. When they see integral of f of 2x dx from a to b, they go, oh, that's just big F of 2x from a to b. And that is wrong because I can't do my rule. My rule is only with a single x. So you would have to go, oh, since it's inside this function and I don't know what the function is, I got to take the 3x, make it a u. My d was a 3. I've got to go, all right, I need a 3 there and a 1/3 there. And I got to make my substitutions and not forget that 1/3. Now what can I do? Does this have a fundamental, can I use my fundamental rule now? I mean, x dx, u du, same thing. So I would have 1/3, big F of u from A to B, and now I can plug the 3x back in there. So now I can say, all right, plug the B in, big F of 3B, plug the A in, big F of 3A, and distribute my 1/3 through. Distribute the 1/3 through. Be a little careful about that kind of stuff. And then one of the other things I wanted to talk about, whether you have an Inspire or whether you have a TI, I might not have updated this in a while. Okay, so if you have an Inspire, your calculator can actually integrate definite integrals. It cannot integrate regular integrals that have like the plus c at the end. It can't give you the new function. It can actually graph the integral function, and it can graph a derivative function, but it can't write it out for you. But it can find a definite integral. So if you have an Inspire, see if you can do this. Go to the screen where you make calculations, right? And just go to the menu button. This is, and I'll talk about a 84 in a second. Go to the menu button, hit calculus, which is normally number 4, but it might be different if you have a newer calculator. And we're going to be doing a numerical integral. So hit the number 2, and an integral pops up. So all you have to do at that point is enter your lower bound, your upper bound, put your function in there, and remember to make your dx variable match your other variable. Hit enter, bam, you get the number. Now, if you have an 84, sorry. If you have an 84, all you got to do, you know, with the derivative, you go math 8, and you have the derivative, math 9. If you ever hit math, you can scroll down or see at the bottom, it says fn int. That means the integral function. But when you hit 9, you see the integral pop up, you do it the exact same way. Now, I will say that entering stuff here is trickier on an 84. Let me just give you a quick example. Watch this. If I asked you to integrate this from 3 to 5 of x plus 2 squared dx, try typing this in with an 84. Plug the 3, you go to the 5, and when you type in the x plus the 2 and you try to go outside of that parentheses, it doesn't let you, does it? Do you see that? Like you're trying to, and you're like, I can't get outside the parentheses. It just jumps right to the dx. So what you have to do, when you want to put this in there, you got to put that whole thing inside of the parentheses of your 84. So you actually got to put an extra parentheses, then do x plus 2, end it, then square it, and then go outside and do the dx. And your answer should be 72.667 if you were rounding. But you'll see with an Inspire, and there are a couple other ones that become tricky. With an Inspire, it's not bad at all. You plug a 3, you go up and do the 5, you go up and do the 5, and when you come down, when you start typing x plus 2, it immediately puts a parentheses, doesn't it? As soon as you hit plus, it throws a parentheses in there, and then all you can do, you can only, if you square it, watch this, go behind the 2 and square it, and it's only going to square the 2. So be careful on both of those. X plus 2, if you put your own parentheses in there, it allows you to square. You see the difference? Like for instance, if I'm looking at this on an Inspire, and I have that done, if I just do x plus 2, it puts the parentheses, and it will not let me square it. Okay? But if I do this, watch this. If I type in right now, this is what I'm looking at on an Inspire. Right there, if I'm on right there and I just hit parentheses, then it allows me to do this. If I enter my own parentheses, it allows me to type that in and then put a 2 there. X plus 2, go out, square it, dx. And it gives me the same thing. And remember, 3 decimals. Y'all with me so far? Okay, so right here, some classwork. What do we got? How much time? 4 minutes. We'll try to do just a couple of these. I'm going to jump around. What about number 2? What is the integral of this? Partially this, 3x cubed over 3, which is x cubed, minus 2x squared over 2, which is minus x squared, minus x. Now, what did we say we had to do for AP? We have to put that with a bar on the right, -1 to 3. Now, if you do that, then really you can do all the other math in your head. You can plug a 3 in and go 27, minus 9 is 18, minus 3 is 15. That's fine. You could plug a -1 in and go -1 minus +1 is -2, plus 1 is -1. Put that in there, 15 minus -1 is 16. I'm not encouraging that. I think it would probably be better for your brain if you wrote 3 cubed minus 3 squared minus 3, and then -1 cubed minus -1 squared minus -1. It probably would be easier to actually see the math. All right, 27 minus 9 minus 3, and then go -1 plus 1 plus 1. Oh, absolutely, because look at that. No, that's a -1. So -1. Do that math separately, probably less errors. But AP needs to see that, or that, right there, and that. Okay? I always do both if I was taking this test. What about number, we got 2 minutes. What about number 4? How would you integrate number 4? Do what? Do I have to do U substitution on this? Or could you just say, this is 2x to the -2 over 3? Couldn't I do that? So what's the integral of this? X to the -1 over -1? So I get 2/3 x to the -1 over a -1 from 5 to 10. Now I kind of want to clean that up. Can you clean that thing up? Throw the x on the bottom and call it -2/3, -2 over 3x from 5 to 10. I'd probably do that. And then here it is. I'm plugging the 10 in. I'm plugging the 5 in. Plugging a 10 in gives me -2 over 30, which is 1 over 15. Plugging a 5 in gives me -2 over 15. And a -1 over 15 plus a 2 over 15 is a 1 over 15. But notice I showed my rule, had my answer, had the little vertical line in there. Hey, see what you can do, guys. Do the best you can. And we'll talk about some of this other stuff tomorrow because we ran out of time.
Sir, you should understand my ADD courses.
No, I was squirrel occasion.
If it's in size 4,